When statisticians do hypothesis testing, they usually use what's called t-tests. It's a lot more general. What we've done before, we're very, very limited. We're gonna be able to extend it a little bit today. So we're going to learn about the t-tests. It's just doing more in the way of testing. The philosophy, the concepts of hypothesis testing are just what we did before. And the mechanism is the same, just the details are a little more specific now. We're going to first let me define a two-sided hypothesis by giving an example. We said last time we talked about the mean height. The mean height was 72. When your null hypothesis says that the mean height is 72, the natural alternative hypothesis is that it's not 72. This symbol means not. It's not equal to 72. It's something else. And we call this a two-sided hypothesis because I would reject the hypothesis if I believed, for example, that the true height were 80. If I thought the fellow was 80 inches tall, really 80, I'm convinced he's 80 inches tall, then I would say the null hypothesis is wrong. I would reject it because 80 is much bigger than 72. On the other hand, if I thought that the true height was 50 inches, he's only 50 inches tall, I would reject the null hypothesis because 50 inches is much smaller than 72. So I could reject this hypothesis on either side. And I call this a two-sided hypothesis because I can reject on either side of it. Okay? We've already seen how to make 5% and 1% level tests. And in fact, this is what it is. If you write it out, what it was is you say the mean is between x bar minus something and x bar plus something. And what that something is a number like 1 or 2 for 5 and 1% level test, 1 and 2, times s divided by the square root of n, which is the standard error. So this is actually how you do the hypothesis testing, where you put 1 or 2 in here for the t star. Okay? Now, this is called a two-sided test of this two-sided hypothesis. If you have a two-sided hypothesis, you make a two-sided test. And what happens if the value you get is bigger than your interval? You reject. If this is outside your interval here, you reject. If it's outside your interval there, you reject. So if the interval was 50 to 60, you'd say, oh, 72 is too big. If the interval were 80 to 90, you'd say, oh, no, 72 is too small, and you would reject. A two-sided hypothesis. Well, we can do that for 5%, 1% level tests by making a 95% or a 99% interval. But what if someone asked for a 10% level test? And that's a standard level to ask for, a 10% level test. Well, clearly, 70% level test is 2 and 3 standard deviations. I said 1 and 2, I meant 2 and 3 standard deviations. So this is either 2 or 3, depending on whether you're using 5 or 10. If you used 1 here, you'd only be 70% sure. You'd be making a 30% level test. That would be pretty bad. A 30% level test would not be a very good test, and people wouldn't do it. But if you were, you'd use a 70% confidence interval, and for that, t would be 1. If you used a 95% confidence interval, t would be 2, and if you used a 99% confidence interval, t would be 3. Well, that kind of means if you want a 90% interval, it's somewhere between 1 and 2. Right? Somewhere, maybe 1.8 or some number between 1 and 2 might give you a 10% interval. But what is that number? Well, we're going to see. We're going to see in a moment. But first, I want to talk about one-sided hypotheses. Let's say someone were to say, oh, John is at least 6 feet tall. Means he's at least 72 inches tall. The alternate hypothesis is that he's less than 6 feet tall. I would only reject on one side. If I thought I was convinced that he was 5 feet tall, I would reject the hypothesis that said he's at least 6 feet tall. But if I found out that he was 7 feet tall, the null hypothesis says he's at least 6 feet tall, I'd say, hey, you underestimated it, but you're right, he's at least 6 feet tall. So I could only reject, in this case, if I believed it was smaller than this. This is a one-sided hypothesis. The other one-sided hypothesis, they might say, oh, John he's not 6 feet. He's no more than 6 feet tall. Well, that's one-sided, because if I found that I believed he was 5 feet, I'd say, you're right. He's less than 6 feet tall. He's no more than 6 feet tall. He's 5 feet tall. If I found that he was 7 feet tall, I'd say, no. He's not less than 6 feet tall. He's 7 feet tall. You're wrong. I could reject. I can reject on one side, and therefore it's a one-sided hypothesis. And in order to solve it, the solution is one-sided intervals. And that means intervals of the form. I'll show you how. For this kind of hypotheses, I use this kind of interval. I use only one side. Unfortunately, this is not the same numbers we had before. 1, 2, and 3 don't work. But at any rate, if the null hypothesis is that he's at least 6 feet tall, then I would make a confidence interval by taking x bar plus a t-value, which I will show you in a minute, times the standard error. And I would give one number. I would say, here's my interval. Mu is less than some number. Let's say I knew mu was less than 52. If I said mu is less than 52 and the null hypothesis was that mu is greater than 70, I would reject the null hypothesis. If, on the other hand, I found out that mu is less than 82 and he says mu is greater than 72, I'd say, well, no sweat there. If he's less than 82, he could also be greater than 72. There's no conflict, and I must fail to reject. So I would reject the null hypothesis only if the number was not in the interval. Now that's the interval you would use for this kind of hypothesis. For this kind of hypothesis, that is, someone says that he's less than 72 inches, the alternate is that he's greater than 72 inches. The interval I would use is that mu is greater than x bar minus t, and I'll have to tell you what t is, times the standard error. This is half of the interval. Remember, the interval had two sides to it. It was this side and this side. Well, we're using this side for this kind of hypothesis, and we're using this side for this kind of hypothesis only one side. Well, all that's left now is to do an example and to give you the values of t. Well, here's an example. Let's say someone says that Bill is less than 66 feet tall. 6 feet or under. He's certainly no more than 6 feet tall. The ultimate hypothesis is he's more than 6 feet tall. Okay, we want to disprove that he's less than 6 feet tall by going out and getting some measurements. Our measurements had better all be better than 6 feet, or else we're not going to be able to convince anybody. They'll say, hey, you just fluked. He really is less than 6 feet. So let's say we want to make a 10% level test. That means we have to have a 90% confidence. One-sided interval, 10% level test. Boy, we're really lousing things up. Let's say there are 20 observations in our sample, and x bar is 73. Well, you see already the null hypothesis is looking fishy, but that doesn't make it fishy. It could be within, we have to be really sure. We don't believe it's true, but we have to really be sure that it's not true in order to reject. Standard deviation is 2, and S is 2. That means S over the square root of n, which we'll have to figure out, is the standard error. But the t-value, and I'll show you how to get the t-value, is 1.33 for this situation, 1.33. So we have all the ingredients we need. Write this down somewhere because we're going to use them. We're going to use them in making the test. Here's how we do it. We make the interval. The appropriate interval for that kind of hypothesis is this one. Plugging in the numbers, over here we have 73. For t, we put 1.33. For s, we put 2. For n, we put 20, the square root of 20. We calculate the square root of 20, divide it into that. And we end up with mu is greater than 72.4. Mu is greater than 72.4. The null hypothesis was that mu was less than. Here's mu is 70. Here's 72.4, and the null the interval says that mu is somewhere bigger than that, much bigger, from 72.4 up. The null hypothesis says it's 72 or less. The null hypothesis and the interval we get don't overlap. Therefore, I am 90% sure. 90 because that's the confidence we use, 90. I am 90% sure that 72 is wrong. And anything less than it is wrong. In fact, I'm 90% sure that 72.4, anything less than 72.4 is wrong. Well, if I'm 90% sure it's wrong, I can reject the hypothesis at the 10% level. So I reject this hypothesis at the 10% level. Okay? Now, values of T star. Now, I better explain this. I'm going to talk about confidence intervals. You know how to make tests using confidence intervals. These are the T values. This is for a two-sided 90% interval. This is a one-sided 90% interval. This is a two-sided 95% interval. This is a one-sided 95% interval. This is a two-sided 99% interval. And this column is for a one-sided 99% interval. And the values in here are T, but the values here are N. It depends on M. And I've given you 5, 10, 20, and 100. Your value will be somewhere in between. Well, you can sort of go in between. For instance, what we just used was a 90% one-sided interval with N of 20, and T was 1.33. Remember that? T was 1.33. Well, had we had a two-sided interval, T would have been 1.72 for a 90% interval. Notice that we're being exact here, and instead of 2 would be something like 30. When you have 30 observations, then the normal is pretty close to what it's supposed to be. 2 would be somewhere about 30 observations would mean 2's correct. And for 99, 3, you really have to have lots and lots of it to get 3. It's really less than 99. So the numbers we've been using, 2 and 3 and 1, are not exactly correct. But they were good enough. They're good enough for our quick draw Magora. But right now we're trying to be exact here, and we're trying to one- and two-sided. And let's say instead of 10 or 50, if someone had said 10, one-sided 10, you would pick 1.37. But let's say someone said, I want 15. Sort of go in between there. That's pretty close. I would say 1.035. I would use 1.35 for T star at 15, 90, one-sided interval. So that's how you would use the table. And this pretty much covers hypothesis testing, because all we ever really do is 90, 95, or 99, and one- or two-sided intervals. And here are the T values that you would need. Okay? Now, that's how you do it by hand. Statisticians don't usually do that. What they do is use a computer package. And in this case, I'm going to show you how to use a package called Minitab. And we'll be using Minitab again. You don't have to use Minitab. I just want you to see how statisticians, people who do this, would go about doing it for you. They really wouldn't do it by hand. Here's the data. They put the data in a column called C1. And they say, okay, Minitab, make a t-test, test 47, that's the null hypothesis, with the data in C1. So use the data in C1 to test. You don't have to remember all this. I'm just explaining what it is. Test the null hypothesis 47. The alternative is -1. The alternative -1 indicates that you want to make a test of that mu is equal to 47 or greater, equal to or greater than 47, against the alternative that it's less than. The -1 tells it that the alternate hypothesis is less than, so it's a one-sided hypothesis. You're really testing the mean is greater than or equal to 47 against the mean is less than 47, and it does it. It gives you some information, but the important thing that it spits out is this right here. That's all anyone making these tests has to look at. The p-value is 0.08. Now, what is a p-value? That's what we want to learn at this moment. What is a p-value? Because that's what we're going to be using later on. We're going to be using p-values when we see output from a computer. The computer doesn't ever say reject or fail to reject. It says p-value. In this case, p-value of 0.08. What does it mean? Well, p-value. You can reject any level larger than the p-value, but must fail to reject for any level smaller than the p-value. So remember, we had p-value was 0.08. You can reject at any level larger than the p-value. Well, if someone said make a 10% level test, 10% is 0.1. 0.1 is larger than that. So if someone said the size of the test, often called alpha, the size of the test is 0.1, I would say reject. If someone said make an alpha level test 0.05, a 5% level test, I would have to say fail to reject. Someone said, make a test 0.01, a 1% level test. This is also smaller than the p-value. I must fail to reject. So given the p-value, I can quickly determine whether I should reject or fail to reject at any level or size of a test. And that's how we're going to be doing it when we use computer programs. We, in the class, will not have to go to computers and use computer programs, but we will be seeing output, and people will be showing you output. When you're out there working in the real world and you tell someone to do something, they're going to come to you with their computer output and put it on your desk, and you've got to look at it and, oh yeah, that's nice. And it'd be nice if you could interpret what the things in it mean. And we're gonna be doing some of that. We're gonna let you see computer output and let you interpret some of the things that mean. The most important part when you're doing hypothesis testing will be the p-value. And it'll be one little number. It'll say p-value or some other label that's like p-value. You see that number, and you can quickly in your head determine whether you should reject or fail to reject at any level you like, even if it was an odd level like 13% or 19% or 4% or 2%. You can make any level you like. Generally speaking, people will use 90, 95, and 99. Okay? So you've learned one-sided hypotheses, two-sided hypotheses, how to make them using the chart, and how to interpret the output from a computer program. Have a good day.